Welcome to the lecture Optimization for Artificial Intelligence. This is your lecture 13th in the PhDAI730 series of lectures. We will explore the advanced optimization techniques that form the backbone of modern artificial intelligence. Optimization is a critical component in artificial intelligence as it involves adjusting the parameters of models to minimize errors and improve performance. We will focus on both convex and non-convex optimization, two fundamental approaches that address different types of problems in AI. Convex optimization deals with problems where the objective function is convex, meaning it has a single premium point, which simplifies the process of finding an optimal solution. This type of optimization is widely used in machine learning for tasks such as linear regression, support vector machines, and logistic regression, where the goal is to find best fitting model parameter, efficiency, and reliability. Optimization is the engine that makes artificial intelligence work. Without it, an AI model would be nothing more than a collection of random numbers with no ability to learn or make meaningful predictions. Think of optimization as the process of fine-tuning every single dial and knob inside an AI system until the machine produces the most accurate results possible. Every time an AI model makes a wrong prediction, optimization algorithms step in to figure out exactly how to adjust the internal settings so that the same mistake is less likely to happen again. This process happens millions of times during training, gradually transforming a system that initially knows nothing into one that can recognize faces, translate languages, or recommend movies with impressively big accuracy. What makes optimization so fascinating is that it sits at the intersection of mathematics, computer science, and real-world problem solving. The challenge is never simply about finding the right answer once, but about doing so reliably and efficiently across enormously complex problems with countless variables interacting simultaneously. Different AI tasks require different optimization strategies, much like different sports that we watch at TV, in case of, if we take an example of sports, require different training regimens. A sprinter and a marathon runner both need to be fit, but their preparation looks completely different. Similarly, optimizing a simple linear model and optimizing a massive neural network requires fundamentally different approaches, tools, and theoretical foundations, making optimization one of the richest and most actively researched areas in all artificial intelligence. So here's a research question for you that you can ponder upon, and that is how we can develop unified optimization frameworks that automatically select the most appropriate algorithm based on problem structure, data characteristics, and computational constraints without human intervention. So a sprinter and a marathon runner both need to be fit, but their sporting regimen or exercise regimen are different altogether. Let's look into convex optimization. Convex optimization is the gold standard of mathematical problem solving because it comes with a remarkable guarantee that most optimization problems simply cannot offer. When a problem is convex, any path that follows the downhill direction will eventually lead to the very best solution, no matter where the journey begins. There are no traps, no dead ends, and no misleading detours. This property makes convex problems not just solvable but reliably solvable, which is enormously valuable in fields like machine learning, where practitioners need confidence that their algorithms will find the best possible model parameters every single time they run the training process. The practical impact of convexity on machine learning cannot be overstated. Many foundational algorithms that power real world artificial intelligence applications are built on convex optimization principles, which explain why they are so dependable and well understood theoretically. Support vector machines, logistic regression, and many signal processing techniques all benefit from convex formulation that guarantee optimal solutions within predictable time frames. Researchers and engineers designing new AI systems often work hard to reformulate their problems as convex when possible, even if doing so requires simplifying assumptions precisely because the guarantees of convexity are so valuable. Understanding which problems are convex and which are not is therefore one of the most important skills in applied mathematics and machine learning. So, I would strongly suggest you to conduct a little research on convex optimization. This is a significantly important topic. Non-convex optimization is where the mathematical landscape becomes genuinely treacherous and fascinating at the same time. Unlike the smooth, bowl-shaped terrain of convex problems, non-convex problems resemble rugged mountain ranges with countless valleys, peaks, and plateaus scattered throughout. An algorithm searching for the lowest point in this landscape might descend confidently into a valley, declare success, and never realize that much deeper valley exists somewhere else entirely. This possibility of getting stuck in suboptimal locations is the defining challenge of non-convex optimization, and it is a challenge that has no perfect solution, only clever strategies for managing the risk. Despite its difficulties, non-convex optimization is absolutely unavoidable in modern artificial intelligence because the most powerful models are inherently non-convex in their structure. Deep neural networks, which have transformed fields from computer vision to drug discovery, are fundamentally non-convex systems where the relationship between parameters and predictions involve complex layered transformation that create immensely complicated objective functions. The surprising discovery that has driven the deep learning revolution is that despite this theoretical difficulty, practical algorithms work remarkably well in most real world use cases. Understanding why this happens, when it might fail, and how to improve reliability is an active and important area of research that sits at the frontier of both theory and practice. So, the training deep learning models for speech recognition requires navigating non complex loss landscapes with billions of parameters where optimization algorithms must escape poor local minima to find parameter configurations that accurately transcribe spoken words. So here's a research question for you to ponder upon and look at Google Scholar or IEEE Explore. What theoretical frameworks can provide convergence guarantees to good enough solution in non-convex optimization, and how do we define what constitutes an acceptable local minimum for practical applications? Gradient descent algorithm. Gradient descent iteratively updates parameters by moving in the direction opposite to the gradient of loss function. That step size controlled by learning rate, following the steepest descent path toward minimum point. Linear regression models predicting house prices from features like size and location use gradient descent to iteratively adjust coefficients, reducing predictions errors on training data until convergence to optimal weights. The research question for you to ponder upon is how can we develop adaptive learning rate schedules that automatically adjust step sizes based on local curvature and convergence progress without requiring manual tuning or expensive line search procedures. SGD, or stochastic gradient descent, approximates a true gradient using a single random training example or small batch at each iteration, dramatically reducing computational cost per update while introducing noise that can help escape shallow local minima. Training recommender systems on millions of user movie ratings uses SGD to update model parameters after each small batch of ratings, enabling learning from massive datasets that don't fit the memory. Momentum based methods. So, momentum based methods accumulate a velocity vector that from past gradients that accelerate movement in consistent directions and dampens oscillations analogous to ball rolling downhill that gains speed and smooths out bumpy terrain. Training computer vision models to detect pedestrians in autonomous vehicles uses momentum to accelerate convergence through flat regions of the lost landscape and reduce zigzagging in narrow valley between parameter dimensions. So, can we theoretically characterize the optimal momentum coefficient as a function of local Hessian eigenvalues and develop second order methods that automatically adapt momentum to local curvature? That is a question that you can ponder upon. So, SGD by itself is a very huge area, and I suggest you to conduct research on that. Whereas the momentum based methods is another area that I would suggest you to look into in depth. The practical impact of momentum on training speed can be dramatic. Networks that take thousands of iterations of converge the plane gradient descent often converge in hundreds of iterations with momentum simply because the algorithm stops wasting time oscillating and instead maintaining focused progress toward better solution. The momentum coefficient controls how strongly an algorithm remembers its history, with higher values creating more persistence but also risking overshooting when the algorithm needs to change the direction. So this is another area that I suggest you to look at very carefully, because this will allow you to learn in more depth the deep learning. The ADAM optimization. ADAM is adaptive moment estimation. Combines momentum with adaptive learning rates for each parameter, maintaining running averages of both gradients and squared gradients to automatically scale updates based on parameter specific histories. Natural language processing models like transformers for machine translation use ADAM to handle the varying scales and update frequencies of different embedding dimensions, automatically adjusting learning rates for rare versus common words. The research question for you is to ponder upon is how can we modify ADAM to provide convergence guarantees in non-convex settings, and what theoretical conditions ensure that adaptive learning rates don't interfere with convergence to good solutions. So that's another area that I would suggest you to look into. So what, in my opinion, what makes ADAM particularly appealing to practitioners is its robustness across a wide variety of problems and architectures. While carefully tuned SGD with momentum can sometimes achieve slightly better final performance on specific problems. ADAM typically works well without extensive hyperparameter tuning, making it the default choice when researchers want reliable results quickly. The bias correction mechanism addresses a subtle but important issue where early in training and moving averages used to track gradient history are heavily biased towards zero, because they start from zero, and correcting for this leads to more appropriate step sizes during the critical early phases of training. Despite its widespread success, Adams still has theoretical mysteries, particularly regarding its convergence behavior in non-convex settings and its sometimes unexpected tendency to generalize slightly worse than SGD on certain vision tasks. The convexity properties, checking whether a portfolio optimization problem with risks, constraints is convex, determines whether standard solvers can guarantee finding the global or globally optimal asset allocation in polynomial time. Can we develop efficient algorithms to test convexity of complex composite functions arising of modern machine learning, or characterize when common operations preserve to destroy complexity? Now that's a question that I would suggest you to look into. The Lagrangian duality converts constrained optimization problems into unconstrained ones by introducing Lagrange multipliers for each constraint, providing both theoretical insights into optimality conditions and practical solution methods. Training neural networks with fairness constraints that ensure equal treatment across demographic groups uses Lagrangian methods to balance predictive accuracy against fairness violations, optimizing both simultaneously. So Lagrangian by itself is an area that I suggest you look into this, because the duality perspective that emerges from the Lagrangian framework reveals deep connections between the original problem and a related problem viewed from opposite angle. Rather than thinking about minimizing the objective while satisfying the constraints, the dual problem thinks about maximizing a lower bound on the optimal value by choosing the constraint penalties optimally. So that's another area that I would suggest you to look into this. The Newton's method uses second order information, the Hessian matrix of curvatures, to take larger, better directed steps than gradient descent, achieving quadratic convergence near the optimum but requiring expensive Hessian computation and inversion. Calibrating statistical models with thousands of parameters for climate prediction uses Newton's methods to quickly find maximum likelihood estimates, leveraging curvature information to converge in far fewer iterations than first order methods is another area that you can look into. Coordinate descent optimizes one variable at a time while holding all others fixed, cycling through coordinates until convergence. Simple to implement and often surprisingly effective despite appearing inefficient. So lasso regression for genomic feature selection uses coordinate descent to update one gene's coefficient at a time, exploiting closed form solutions for single variable subproblems to efficiently handle datasets with millions of genetic markers. That's life sciences example. Proximal gradient methods handle composite objective smooth plus non-smooth parts by alternating between gradient steps on the smooth component in proximal operations and non-smooth component, unifying algorithms for diverse regularization penalties. So image diagnosing with total variation regularization uses proximal gradient descent. That's your practical example, taking gradient steps to match the observed noisy image, while proximal steps enforce smoothness through the non-differentiable total variation penalty. So the research question for you is to ponder upon is, can we develop proximal operators for complex structured penalties arising in modern deep learning? Group sparsity, low rank constraints, that maintain computational efficiency while preserving convergence guarantees. So that's a good area that you can jump into. ADMM. So now the good question is, what do you think ADMM stands for? Because that is something that I would like you to figure out. That is alternating direction method of multipliers. So this ADMM decomposes optimization problems into smaller subproblems that can be solved separately and in parallel, coordinating solutions through dual variable updates, particularly powerful for distributed optimization across multiple machines. Training federated learning models across millions of smartphones using ADMM to allow each device to optimize locally on private data, then aggregate updates through a central coordinator without sharing the raw data. So the good question is, how can we analyze ADMM? Convergence rates for non-convex problems common in deep learning, and develop adaptive penalty parameters. Selections that accelerate convergence without manual tuning. So think about it and let's see what you come up with. Constrained optimization requires solutions to satisfy both the objective function and additional quality or inequality constraints, introducing challenges of feasibility, maintenance, and constraint handling during iterative updates. Robot motion planning must find the fastest path while satisfying physical constraints, joint angle limits, collision avoidance, torque bounds, requiring optimization algorithms that respect these hard constraints throughout the search process. So think about it. KKT. Now you might be saying what KKT actually means. It's the Korosh-Kuhn tracker. The KKT conditions represent the fundamental language for describing optimality in constrained problems, extending the simple idea that minimum must have zero gradient to the more complex settings where boundaries and constraints define the feasible region. So verifying whether a proposed solution to a large-scale power grid optimization, so power grid is where we get our electricity from. So let me repeat. Verifying whether a proposed solution to a large-scale power grid optimization problem is truly optimal involves checking KKT conditions, relating generation costs, transmission constraints, and demand requirements across thousands of nodes. So this is another area that you can explore. Saddle point in non-convex optimization. Saddle points are stationary points where the gradient is zero but that are neither local minima nor maxima. Some directions curve upward, others downward, creating plateaus that can trap optimization algorithms. Training generative adversarial networks involves finding saddle points of a min-max game between generator and discriminator networks, where standard gradient descent can cycle indefinitely without converging. Loss landscape geometry. The loss landscape describes how the objective function varies across the high-dimensional parameter space, with topology including valleys, ridges, plateaus, and basins that fundamentally affect optimization, difficulty, and algorithm performance. Analyzing with some neural network architectures train easily while others struggle involves visualizing their loss landscapes, revealing whether they have smooth paths or good solutions or are riddled with obstacles and disconnected regions. So can we characterize architectural choices like depth, width, skip, connections that provably create more favorable loss landscape geometry, reducing the number of poor local minima or widening basins around good solutions? So that's a good question that you can ask. Convergence guarantees specify conditions under which optimization algorithms are proven to reach solutions of certain quality, global optima, local minima, stationary points, within the bounded numbers of iteration or time. When deploying AI systems for critical applications like medical diagnosis, convergence guarantees ensure that the training process are actually find reliable model parameters rather than getting stuck in poor solutions. Learning rate schedules systematically decreases the step size during optimization, starting with large steps or rapid progress and transitioning to small steps for fine tuning, balancing exploration and convergence precision. Training large language models uses sophisticated learning rate warm up followed by cosine decay, initially increasing learning rates to stabilize early training, then gradually decreasing to refine billions of parameters toward optimal values. Regularization in optimization. So, regularization adds penalty terms to the objective function that discourage overly complex solutions, effectively constraining the optimization to find simpler models that generalize better to unseen data despite potentially higher training error. Training image classifiers with millions of parameters on thousands of examples uses L2 regularization, as we discussed earlier, to prevent memorization of training images. Instead, learning generalizable visual features that work on new photographs. Here's your research question. How do implicit regularization effects of optimization algorithms like STD's bias toward flat minima interact with explicit regularization penalties, and can we unify these perspectives into comprehensive theory? Now, that's the question that I would suggest you look into. Future directions. Emerging directions include neural architectures, search that optimizes model structure itself, meta learning optimizers that learn to optimize quantum optimization algorithms, and optimization under distributional shift and adversarial perturbations. AutoML systems automatically design neural network architectures by treating architecture choices as optimization variables, searching through billions of possible designs to find models that maximize accuracy while minimizing computational cost. So I would suggest you to conduct research on this to understand in more depth how AutoML helps. And let's continue in the next lecture.